Okay, so the first sort of a special sort of arrangement of things or method of counting is called permutations. And what these are going to be are basically uh, more or less you can think of them as ordered arrangements of objects. And we've already seen two examples of these. So just some sort of motivating examples. Uh, One was taking a quiz, and here we had three problems, and the question was how many different ways uh, can I go through those three problems. We saw that it was 3 times 2 times 1, which is 6 ways, and notice that this is just 3 factorial, 3 different ways of taking this. But this is an ordered arrangement of objects. I'm ordering the 3 different problems in a particular order to complete them. The second example was, again, locker or lock combinations. And here we're choosing 3 numbers, and this was from 1 to 40. We saw that the possibilities here were 40 times 39 times 38. Now, I could notice that you know, a way of, this is almost a factorial, but what it's missing is 37, 36, 35. So what if I were to multiply this by 37 factorial over 37 factorial? Well, then the top would be 40 factorial divided by 37 factorial. Okay, great. So this is maybe a little bit more compact way of writing things, and in fact, this is going to be a more systematic way of writing things for us. So this is what we get. Okay, so here's our formula. And if we choose or arrange, I'm going to write, I'm going to use the letter K, K objects from a group of N objects, total objects, and if the order that we choose or arrange them matters, the total number of ways of making all the choices, of ways of making all the choices are the arrangements, is given by, we write it down like this. We write N, P, K, that's the notation the book uses. I think I might use the letter R, but my letters R and N look kind of the same, so I'm going to avoid that. And it's N times N minus 1 times all the way down to N minus R plus 1. Why? This is how many choices I have for the first guy. This is how many, N minus K plus 1. This is how many choices I have for the second guy. I keep going down. This is how many choices I have for the kth guy. The plus 1 is there. It's just a little weird that it's there. But we can rewrite this formula a little bit more nicely, which is n factorial divided by n minus k factorial. So that's a little bit nicer of a way to write this. So in fact, I suggest maybe you try to remember this way. Okay. So let's look at some examples of using this. So first, let's look at, say, horse racing. Now, I was trying to find if there's like a standard number of horses that typically end up in, say, like the Kentucky Derby or something like that. But it looks like it might vary from year to year. But let's just assume that we have 20 horses in a race. And There's a particular sort of bet called the trifecta. And what the trifecta says is this. The trifecta says to win, I have to choose the horses in first, second, and third places. So, okay. So I am choosing k equal to 3 horses out of n equal to 20. So how many trifecta bets are there? Well, the total number of trifectas there is p of 23, a 20p3, which by the formula is 20 factorial divided by 20 minus 3 factorial. Now let me just note here, when computing 20 minus 3 factorial, it's not something like this. It's not 20 factorial minus 3 factorial. I have to compute what's on the inside first. So what I really get is 20 factorial divided by what's 20 minus 3, 17 factorial. And 20 factorial, let me write this out, 20 times 19 times 18 times 17 factorial divided by 17 factorial is what that is. I'm writing it out like this so that I can cancel these guys out. And I'm just left with 20 times 19 times 18, which I've already computed off to the side. This happens to be 6,840. So that is the total number of ways that I could choose a trifecta. The horses in first, second, and third place out of 20 horses. Cool. Another example. Let's suppose I'm putting together a test and I have 15 possible questions, but I only want to put on 10. And the thing is, the order matters when I make a test because I have to, say what's problem number 1, problem number 2, and you get very different tests depending on, how I arrange the questions. If I arrange them hardest to easiest, that feels a lot different to you than if I arrange it easiest to hardest. So the order matters in terms of how you're taking the test or how I print it up or whatever. So here I'm choosing 10 problems out of 15 total possible problems. And so the total number of tests is going to be the total number of possible tests that I can make up is given by 15p10, which is 15 factorial divided by 15 minus 10 factorial, which is 15 factorial divided by 5 factorial. Now when you get to some numbers like this, it's probably best to use a calculator. But depending on what sort of calculator you have, you may or may not be able to actually write all of these numbers out. So you get 1, 3, 0, 7, 6, 7, 4, 3, 6, 8, 0, 0, 0. That's what 15 factorial is. It's that huge number. 5 factorial we've seen a couple times, and that's 120. So if I take that big number on top and divide it by 120, I still get a very large number. 1, 0, 8, 9, 7, 2, 8, 6, 4, 0, 0. I'm putting my commas in there. That says it's 10,897,286,400 possible different tests. So that means that even if I put together all the possible different versions of the tests possible, I could give a different version to everybody on the earth. Nobody would have the same exact version. So that way I can make sure nobody's cheating off of each other. Ha! Okay. So that's crazy. I don't really go through all of these different possibilities if I'm putting together a test like that. Great. Let's look at a third example. Let's say I have a student group and it has, let's say, 10 members, and we need to elect a president, a secretary, and a treasurer. Now here it's not obvious that this is necessarily going to be a permutation because where am I putting things in order? Well, we can assume, say, that the order of voting these guys in, I choose the president first, excuse me, then we vote for the secretary next, and then we vote for the treasurer third. So really, I'm choosing 3 people out of 10, and the order matters because of the order that we're voting for them. So we're really choosing k equal to 3 people out of n equal to 10. And here order matters because we're not just choosing 3 people without caring what they are. We have different offices for them each to hold. So what we get the total number of ways of choosing these 3 leaders, so the number of ways of electing officers is 10p3, which is 10 factorial divided by 10 minus 3 factorial. That's 10 factorial times divided by 7 factorial. This one I can actually do by hand. 10 times 9 times 8 times 7 factorial. I write out 10 down to 7, and I stop at 7 because I want to cancel with 7 factorial. I cancel out the 7 factorial, I'm left with 10 times 9 times 8, and if you do out the math there, that's 720. 720 different ways of selecting the officers for this student group. Okay. Now the last one I'm going to do is a bit more difficult than the last couple that we did. Let's say at lunch you're going to sit with 4 people are going to sit at a table with 6 seats. And how many ways can they sit down? So how many ways can they sit? Well, a common mistake here is to say what is being arranged or what is being chosen. The people are being arranged. It's true that the people are being arranged, but it's not like they're being arranged 1, 2, 3, 4, 1, 2, 3, 4. We have 1, 2, 3, 4, 5, 6 slots for the people to fit into. So we're not choosing a subset of the 4 people, we're choosing all of them and putting them into 6 possible different places. So this is not a typical permutation. Instead, what is really being chosen are the seats. The seats are being chosen. And we have, so we're choosing the seats. So the total number of things we're choosing from are 6. How many are being chosen? We have 4 people. So 4 seats out of the 6 are being chosen. Why does the order matter? Which seats are chosen? Well, different people sitting in different seats constitute a different arrangement. So order matters. Since different people, sitting in different seats, gives another arrangement. And so I'll leave this as an exercise to you. Show that the number of ways of doing this is equal to 360.